All right, let's go ahead and get started. So just as a reminder, I encourage you all to attend David Gross's lectures tonight and tomorrow afternoon. They should be a lot of fun. He's a real star, and he gives excellent talks. So I think both of them should be a lot of fun. One other comment of what is it? A comment on the programming rather than on the content of this course. So I went through and I planned the rest of the lectures. I think I'll have an extra one to two lectures at the end of this course that I don't yet have plans for. And so I was trying to decide what special topics I should cover. So the reason why I actually have extra lectures, it turns out, is that this year we're on a Tuesday, Thursday schedule rather than a Monday, Wednesday, Friday. And somehow I get a lot more done when I'm teaching 2 hour-and-a-half classes rather than 3 50-minute classes. So I'm actually a little ahead of schedule. So we have some time to discuss other topics. So today we're going to finish our discussion of Hamiltonian mechanics, and then we'll spend about 3 to 4 lectures on advanced topics in Hamiltonian mechanics. Some exact results: Liouville's theorem, Poincare recurrence theorem, Hamilton-Jacobi theory, integrable systems, and the relationship with quantum mechanics. But it's likely I'll have about a lecture at the end, unaccounted for. So I was considering doing one of two things. I could either talk a little bit about chaos and dynamical systems, catastrophe theory, something like that. The problem is that any discussion of that, all of that stuff it's a little, anything you can present in one lecture is going to be a little vague. So the other thing that I was doing was considering just having a lecture or two on special relativity. So in order for me to decide what to do, how much special relativity do you guys get? I mean, sometimes you end up seeing special relativity again in all these different courses. So you haven't seen it since the first semester. Okay. But you probably will. Did you, in your E&M class, see the electromagnetic field strength tensor? Which you will take. So there's no reason for me to do that. But do you see Lorentz transformations? Do you see the 4x4 matrix of Lorentz transformations? Do you see do you see the line element of special relativity? You don't use that terminology. Okay, so I might say something about comment. Well, what would you suggest? Well, we did do the Kepler problem. We could do the three-body problem. Actually, the three-body problem is we did the two-body problem, which is great. The problem with the three-body problem, of course, is that it's not exactly solvable. That would be sort of fun, actually. I mean, I actually could easily do a lecture on the three-body problem and on that sort of stuff with a relationship to the solar system. That's kind of interesting. So those are probably the 3 topics. Should we take? Do you have a comment, or no? You just are holding up your hand. Okay. Who would prefer to do chaos? Who would prefer to do special relativity? I haven't decided. I don't know yet. That's why. So the answer is no. I have to see if I'll think about it and see if I can prepare a coherent lecture or two on it. I could do chaos. How many people would prefer to see solar system dynamics in the three-body problem? 1, 2. Okay. Maybe I'll try and prepare a lecture on chaos. That would be fun. I've never actually given a lecture on chaos, so I would enjoy preparing that. Okay, so I'll try and do that. One other, let's see. Okay. No, that's all. Okay, enough of that stuff. Let's talk about some physics. So today we will conclude our discussion of the Hamiltonian framework for classical mechanics. I will begin today, as I begin every lecture, by reminding you of the basic formulation of Hamiltonian mechanics. So for a system with n degrees of freedom, we have a phase space, which is a space of positions and conjugate momenta, and the evolution of the state of the system is described by a flow on phase space, which is given by Hamilton's equations, which say that the time derivative, I guess I shouldn't write a bracket there. Let's just call it parentheses, so that the time derivative of Q and P is given by a vector which is, morally speaking, the vector perpendicular to the gradient of the Hamiltonian, regarded as a function on phase space. And this formulation of the evolution of Q and P in the Hamiltonian framework can be rephrased in a very elegant way if one introduces the Poisson bracket between two functions. So if I have a function f of Q and P and g of Q and P, then their Poisson bracket is given by the sum of df by dq times dg by dp minus the same thing with f and g reversed. And this Poisson bracket is the classical equivalent of the commutator of two operators in quantum mechanics. In particular, the positions and momenta obey the fundamental Poisson bracket that the Poisson bracket of Q with Q is equal to 0, the Poisson bracket of P with P is equal to 0, and the Poisson bracket of Qi with Pj is equal to 1 if I is equal to j and 0 otherwise. And one use of the Poisson bracket is the statement that if you have a function of p, q, and possibly time, then the derivative of f with respect to time, so if we want to compute the time dependence of some function of p and q, then that is just equal to the Poisson bracket of f with the Hamiltonian plus an additional term that describes the explicit dependence of f on time. And so, in particular, a constant of motion I of p and q is a function of p and q such that its commutator with the Hamiltonian, its Poisson bracket with the Hamiltonian, vanishes. And finally, last class, we began our discussion of symmetries in the Hamiltonian framework. And we introduced the notion of a canonical transformation which is a transformation of our basic variables that we use to describe the state of the system. So if we started out with some positions and momenta, then we could describe the system in terms of some new positions and momenta that I called capital Q and capital P, which are functions of the old positions and momenta. And the form of Hamilton's equation is unchanged if the Poisson bracket of Qi with Pj is unchanged when we do this transformation. So the Poisson bracket of big Q with big P takes the same form, delta ij, as the Poisson bracket of little q with little p. And these canonical transformations include, for example, transformations of the dynamical variables from linear coordinates, Cartesian coordinates, to polar coordinates, or spherical coordinates, or rotating coordinates, or anything like that. And we described a few examples of canonical transformations, and I gave you a general procedure for constructing a canonical transformation using what are known as generating functions. And in your problem set due on Monday, you'll work out a few examples of these canonical transformations. And the generation of these canonical transformations in terms of generating functions. Today, however, I would like to consider a different aspect of the theory of canonical transformations, which will make it really clear exactly why these canonical transformations are so interesting. So are there any questions before I continue? Okay. So the theory of canonical transformations gets much more interesting if, rather than considering a general canonical transformation, we consider an infinitesimal canonical transformation. So in particular, let's imagine replacing our QIs, reformulating our variables in terms of some new degrees of freedom, big QI, which are equal to little qi plus some very small infinitesimal perturbation. And so I'll call that epsilon, where the epsilon here reminds us, so epsilon is very small and reminds us that we are considering an infinitesimal canonical transformation times EI, where EI is just some function of the Q's and P's. And likewise, the momenta will be given by big PIs, which are just the same as little PIs, plus epsilon times another function that I'll call Fi of Q and P. So, in order for this to be a canonical transformation, the Poisson bracket of Qi with Pj has to be equal to delta ij. So we need to impose this on our canonical transformation. So what equations do the E's and F's have to obey? Well, let's just take that definition of big Qi and big Pi and plug that in to compute the Poisson bracket. So first, we have the Poisson bracket of Qi with Pj. Then we have terms of order epsilon. And what are those terms of order epsilon? Well, we have a term which is the Poisson bracket of Qi with Fj plus another term that's the Poisson bracket of EI with Pj, plus terms of order epsilon squared. And we wish this to be set equal to delta ij in the limit where epsilon is very small. So what that means is that we are neglecting the order epsilon squared terms. We're neglecting the order epsilon squared terms, and we can use the fact that this term here, Qi Pj, just gives you the delta ij. So what we need is the Poisson bracket of Qi with Fj plus the Poisson bracket of EI with Pj should be equal to 0. So what is that Poisson bracket? Well, the first term is the Poisson bracket of Qi with Fj. which is just the derivative of fj with respect to pi. Because the Poisson bracket is of qi with fj would be the derivative of qi with respect to qk times the derivative of fj with respect to pk, which will be 0 unless k is equal to I, so we'll get the derivative of fj with respect to pi, minus an additional term which is 0 because the derivative of q with respect to p is equal to 0. Is that clear? I guess we've already done that computation a few times. And then the other term will be the derivative of ei with respect to qj. So that means in order for this to be a canonical transformation, the derivative of fj with respect to pi has to be equal to the derivative of ei with respect to qj. Okay, so how could we make this occur? So what choices of f and e could we choose such that the derivative of f with respect to p is the same as the derivative of e with respect to q? Well, one way of doing this would be to set fj to be the derivative of some function g of p and q with respect to qj, and ei to be the derivative of some function g with respect to pi. And so you can see that if you did that, then this identity here would be automatically true because of the equality of mixed partial derivatives. Is that clear to everyone? So as long as f is the q derivative of some function g, and e is the p derivative of that same function g, then for any function g that depends on p and q, we can find an f and g such that we have a canonical transformation. So in vector calculus, you're very familiar with this statement. In vector calculus, this is the statement that a vector which is curl-free is equal to a divergence. And this is just the n-dimensional version of that statement. And so I won't prove it to you, but in fact, one can show that any f and g with this property must be given by derivatives of g with respect to p and q. So you guys remember the vector calculus statement that a curl-free vector field is a gradient? Or another, you can just imagine if you have a vector field which is the gradient of a scalar, then the curl of that vector field is equal to 0. And that's precisely for the same reason, because of the equality of mixed partial derivatives. Yes? Well, you could always add to g a constant, and that wouldn't change f and e. So it's not unique. Okay. And so in this case, we have a special function g which is associated with this infinitesimal canonical transformation. And the words we say are that g, which is a function of p and q, generates our infinitesimal canonical transformation where q goes to q plus epsilon times dg by dp, and p goes to p plus epsilon times dg by dq. I'm sorry, there was a plus sign here, wasn't there? And there's a minus sign here, and a minus sign there. I apologize. I knew I missed a minus sign somewhere. Everyone got that? There was a minus sign because the Poisson bracket of E with P was plus dE by dQ. Sorry about that. This is what happens when I write my notes the night before. Okay, any questions on that? So, for any function of phase space, that's any function of Q and P, we can always find an infinitesimal canonical transformation just by taking derivatives of that function and adding it to Q and P. And in the limit where epsilon is small, this will be a canonical transformation. And so in particular, it will be a transformation of the variables that we use to describe the state of the system, such that the form of Hamilton's equations of motion are unchanged. Any questions on that? Okay, so let's start with a very simple example, which will make it clear to you why it is I am considering these infinitesimal canonical transformations. Let's ask the following question. How do the phase space coordinates Q and P evolve with time? Well, Q dot is dH by dP, and P dot is minus dH by dQ. So after a small amount of time dt, Qi will evolve to Qi plus dt times dH by dPi, and Pi will go to Pi minus dt times dH by dQi. That's what it means to say that Q dot is equal to dH by dP, and P dot is minus dH by dQ. It's just the statement that if you ask how Q and P evolve with time, then they evolve to first order in dt according to this formula. So hopefully you can see that something I've written on the bottom of this slide looks awfully familiar to something I've written near the top of this slide. So in particular, we see that time evolution of a dynamical system is the canonical transformation generated by the Hamiltonian. So let's think about that for a second. So if you started with a system with dynamical variables Q and P regarded as functions of time, then I could always take t to t plus a constant. And those would be different functions. Those would be functions of the old Q's and P's. But the form of Hamilton's equations would not change just because I translate in time. So that means that the time evolution of the system, t goes to t plus a constant, is a canonical transformation. And what canonical transformation is it? It is the canonical transformation generated by the Hamiltonian. So there's a sense in which if you regard these canonical transformations as symmetries of the system, time evolution is trivial because it's a symmetry of the system, and it's the symmetry of the system generated by the Hamiltonian. So time evolution in phase space is the canonical transformation which is generated by the Hamiltonian. So in your quantum mechanics class, for example, you learned that wave functions obey Schrodinger's equation. D by dt of psi is equal to the Hamiltonian acting on psi. That is exactly this fact here. It's the statement that time evolution is generated by the Hamiltonian. So this, I think, is one of those truly deep statements in classical mechanics, and it's probably worth thinking about for another few minutes. Are there any questions on this? I should emphasize here that the way that Q and P transform for an infinitesimal amount of time is very simple. Q goes to Q plus dt times dH by dP. But if you wanted to try and integrate this up and try and find out how Q and P transform for a finite amount of time, then of course you need to solve a differential equation. And that differential equation may or may not be easy to solve analytically. But conceptually at least, you know exactly how a system transforms. It transforms according to a canonical transformation. And that canonical transformation is the canonical transformation which infinitesimally is given by the Hamiltonian. Any questions? Okay. So, we learned that one can use the Poisson bracket to compute not just how Q and P evolve in time, but how an arbitrary function of Q and P evolves in time. So, put another way, we already saw that the time evolution of a function of P and Q is given by the Poisson bracket of that function with the Hamiltonian. And the Hamiltonian is the thing that generates the canonical transformation, which is time evolution. So now we could ask another question. So let's say we have a canonical transformation which is generated by some function of P and Q. Then we could ask how some other function of P and Q changes. Well, because Q goes to Q plus epsilon dg by dp, and P goes to P plus minus epsilon dg by dq, we can then understand how F changes to first order and epsilon. So that's just given by Taylor's theorem. So F of P and Q goes to F plus a term of order epsilon, which is the sum of two quantities. So the first comes from the variation of the dependence of F on P. So it's the sum over K of dF by dQk times the variation of Qk to first order and epsilon, which was dg by dpk. And then a similar term which comes from the dependence of F on pk, which is then multiplied by the variation of P, which is dg by dqk, plus terms that are higher order in epsilon. So hopefully that term in the parentheses is boring to you at this point, because we've encountered it magically so many times already over the last few lectures. What we see is that the variation of this function of P and Q under the canonical transformation generated by G is our small parameter epsilon times the Poisson bracket of F and G. For example, if we have the canonical transformation generated by the Hamiltonian, that's time evolution. And so under time evolution, if we take t to t plus dt, then the variation of f is dt times the Poisson bracket of f with the Hamiltonian. Or if I was lazy and didn't use a Greek d but a Latin d and divide both sides by dt, this would be the exact same expression that we derived earlier for the time derivative of a function of p and q. So this statement here is nothing more than the generalization of our previous statement about the time evolution of a function of p and q, except now we're asking how f varies under an arbitrary canonical transformation, not just one generated by the Hamiltonian. Any questions on that? For example, let's say that we have a canonical transformation generated by a function g of p and q. You could ask how the Hamiltonian changes under that canonical transformation. Well, under a canonical transformation, generated by g, the variation of the Hamiltonian is epsilon times the Poisson bracket of h with g. And what is the Poisson bracket of h with g? That's also minus the Poisson bracket of g with h, which was g dot. So, what does that mean? That means that if g of q and p is a constant of motion, which is to say g dot, which is the Poisson bracket of g with h, is equal to 0, then the Hamiltonian is invariant under the canonical transformation generated by g. This is Noether's theorem. Remember, in the Lagrangian setup, Noether's theorem was phrased as follows. If we have a change of variables, little q to big Q, then that leads to a constant of motion. How do you compute that constant of motion? You consider the infinitesimal change of variables, and you ask, and you demand that the Lagrangian is invariant under that infinitesimal change. Here we see that the exact same thing can be understood in the Hamiltonian framework, but instead phrased in terms of canonical transformations. So if we have a canonical transformation which leaves the Hamiltonian invariant, then we can consider the infinitesimal form of that canonical transformation, and it's generated by some function g, which is a constant of motion. This is what I called I last lecture when I was discussing Noether's theorem. But it's even more exciting because we can now understand how to answer the reverse question than that which was asked in Noether's theorem. So Noether's theorem said, if we have a symmetry, what is the conserved quantity? Now we can ask the following. If we have a constant of motion, if we have a conserved quantity, what is the symmetry? And the answer is that the symmetry is the canonical transformation generated by the conserved quantity. So this is Noether's theorem. The symmetry of a system corresponding to a constant of motion g is the canonical transformation generated by g. And in a sense, this is a much more powerful version of Noether's theorem. Because if you happen to find a constant of motion, you can then derive a symmetry of the system, rather than the other way around. So, for example, last time, or maybe it was 2 classes ago, we described the hidden SO4 symmetry of the Kepler problem, corresponding to this additional 3 conserved quantities that we called AI. Now, the thing that was not at all obvious to you when you showed in your problem set that the AIs were constants is what the corresponding symmetry is. Now you can just go ahead and write down that symmetry. It's given by the Poisson brackets of AI with the variables in your system. If you want to know how Q transforms under this symmetry, you take the Poisson bracket of Q with the AIs. And likewise for P. Are there any questions? So, I would like to make one important point here. So, a symmetry is a canonical transformation which is generated by something which commutes with a Hamiltonian. So it's generated by some function of Q and P such that the Poisson bracket of G with the Hamiltonian is equal to 0. And those are a special set of canonical transformations. So given a Hamiltonian, there may or may not be certain functions of P and Q whose Poisson bracket with a Hamiltonian vanishes. Those generate symmetries of the system. But even if a function of G does not have a vanishing Poisson bracket with a Hamiltonian, it still generates a transformation. So even some function of the Q and P's which does not have vanishing Poisson bracket with a Hamiltonian still generates a transformation. So any function of Q and P still generates a transformation. For example, consider the momentum pi. Pi is a function of Q and P, right? It's a very simple function of Q and P. It's almost as simple a function as you could ask for. And pi is the function of Q and P which generates translations in Qi. Why? Well, let's imagine that we had as our generating function something which is linear in the p's. So it would be, say, the sum on I, Ci, pi, where ci is just a set of constants. You could think of ci as a vector. Then, under the canonical transformation generated by G, how does Qi transform? Well, that's epsilon times the Poisson bracket of Qi with G, which is Ci. Right? Because the Poisson bracket of Q with P is equal to 1. So that means that this canonical transformation is the one which takes Qi to Qi plus a constant times Ci. That's a translation in Q. And if you think of Q as a position vector and C as a vector in position space, then it is a translation in the direction of the vector C. And this statement is something that is true independent of whether or not the Hamiltonian is independent of Q. So the statement that P generates a translation is independent of whether or not P is a symmetry, whether or not translations are a symmetry of the system. So even if your Hamiltonian is some very complicated function of Q, it's still the case that your momenta generate translations in Q. So, in your quantum mechanics class, you may have wondered why P is d by dx. And this is the answer. The answer is that d by dx is also an operator which generates translations in x. And that's true independent of whether or not your Hamiltonian depends on x or not. Another example. What's another simple function of P and Q? Well, Q is a simple function of P and Q. Anyone have any guess what the canonical transformation generated by Q is? Someone must have a guess. Don't be shy. The canonical transformation generated by Q is a translation of P. You know, what's the great thing about the Hamiltonian framework? Q and P are treated on equal footing. Any sentence involving a Q and a P is also true if you reverse the P's and Q's in that sentence. Up to minus signs. So just as P generates translations in Q, Q generates translations in P. That's why in quantum mechanics, when you study wave functions in momentum space, the position operator x is d by dp. It's the same thing. Okay, let's do a slightly more sophisticated example. Well, let's say that we have a more complicated function of Q and P. So let's say we have a particle moving in 3 dimensions with position r and angular and conjugate momentum p. Then we could define a vector, which is the angular momentum vector, r cross p. That's a function of phase space. It's a set of 3 functions of phase space. L1 is r2 p3 minus r3 p2. L2 is the same thing with 1, 2, and 3 cyclically permuted, and so forth. So this is a set of 3 functions of phase space. And I could, for example, write down the canonical transformation, which is generated by the function g, which is the sum over k, alpha k, lk. Now, if we want to ask how Q and P transform under this transformation, then we just need to calculate the Poisson brackets of Q and P with G. And I'll just tell you the answer, because it's an answer that you're going to check on your problem set, which is due Monday. And the answer is that the position goes to R plus epsilon times alpha cross R. And likewise, the momentum. Now, let me remind you that the transformation where R goes to R plus epsilon alpha cross R is the infinitesimal form of a rotation by an angle epsilon about the alpha, an axis pointing in the alpha direction. So this is the infinitesimal rotation about the axis alpha. So just as the momenta P generate translations in Q, if you have a three-dimensional system, you could write down the angular momenta, R cross P, and those would generate rotations. And how does R transform under a rotation? Well, it just transforms in the way that a vector transforms under a rotation. R goes to R plus alpha cross R. And P is also a vector. And what do vectors do for a living? What a vector does for a living is it transforms under rotations. That's why they get paid to be vectors. P goes to P plus epsilon alpha cross P. And you'll check this on your problem set. And I think it's really important to emphasize that the vector L generates angular momentum, independent of whether or not a system is rotationally invariant. Now, if a system is rotationally invariant, then L commutes with the Hamiltonian and is a constant of motion, and boy, that's great. That helps you out a lot. But even if it doesn't commute with the Hamiltonian, it still generates a rotation. So one final comment that I should emphasize while we're discussing angular momenta, which is that for a free particle with a normal Lagrangian, P is equal to R dot. And the form of the angular momentum can be written as R cross R dot. But the important thing about angular momentum is that it's the thing which generates rotations. And so the more correct formula for the angular momentum is R cross P. In particular, if you're studying a system where the momentum conjugate to R is not R dot, but is a more complicated function of R and R dot, then the correct form for the angular momentum vector is R cross P, not R cross R dot. This is a mistake that people always make. For example, if you're studying a particle in a magnetic field, then the momentum conjugate to position is not R dot, but is rather some more complicated function of R and R dot. And likewise, the angular momentum vector will be changed as well. Did I do this? Did I give this to you on your last problem set? Okay, good. So you're already familiar with this fact. So, are there any questions on this? Yes.
If you have a time-dependent Hamiltonian, then can you have a symmetry that is likewise time-dependent?
Yes. And even if the Hamiltonian has an explicit dependence on time, time translation is still generated by the Hamiltonian in exactly the way that I've said. Yes, that's a good question. I mean, I think this business about canonical transformations and symmetries and all this stuff, I mean, this is really deep stuff. It's really at the heart of physics. And so I really encourage you to mull over this a little bit. It's probably quite new to you, but these facts really underlie a lot of what has probably heretofore seemed somewhat mysterious to you in your physics careers. So are there any other questions? No questions. Okay. So, at this point, we've really concluded the material that I think is the standard material that belongs in a class on classical mechanics. So, at this point, I'd like to draw a bit of a line between things that we have studied so far in this class and things that we will spend the next 2 weeks or so studying before the end of the semester. So we've completed what I consider the core material in a class on analytical mechanics, classical mechanics. Only the material that we have covered up until I drew this line about 30 seconds ago is stuff that you'll be responsible for on a final exam. Everything above this line is stuff that I consider the core material in a class on mechanics. And that's the stuff on which you will be tested on the final. And everything below this line is what I consider cake. This is fun stuff, which we will spend the next few weeks studying because it's interesting and because it's important. But I think it is outside of what I consider to be the core material in a class on mechanics. So at this point, what we're going to do is we're going to shift gears a little bit. And we'll probably spend the next week and a half or so delving into even more detail on Hamiltonian mechanics. But I'll be presenting things that I think are sufficiently advanced that I think they're probably outside of the scope of what it would be fair to test you on a final exam. So so this is where the line is drawn. Also, I guess now is as good a time as any to mention that the material that corresponds to this line in the textbook stops somewhere in Chapter 6. I don't remember exactly which section in Chapter 6 it is. I wrote it out on the syllabus, and also I'll hand out some practice problems for the final exam, and I'll be very explicit about which sections of the book you will be responsible for. But at this point, our goal for the next 2 weeks is basically to have fun and to try and understand a few more advanced topics in classical mechanics. So are there any questions before I continue? Okay. So what I would like to spend the rest of lecture discussing today, and probably part of next lecture, are two topics which I think are a little bit formal, but they really help us understand intuitively the behavior of dynamical systems. So first, I would like to present a result which is known as Liouville's theorem, or Liouville's theorem. There's a Liouville and a Liouville, and I always get them confused. I think this is Liouville. So let's consider some mechanical system. So this mechanical system will have some positions and momenta, and its time evolution will be described by some Hamiltonian that is a function of the Q's and P's. Now, the standard question that one likes to ask in the study of Hamiltonian mechanics is if you start with an initial configuration, some initial value of Q and P, then what will be the value of Q and P at some later time? Now, of course, that involves solving some differential equations, which we may or may not be able to solve. But, in fact, we can obtain some intuition for the answer by asking a slightly different question. So rather than asking the question, how does an initial configuration evolve with time, I would like to ask the following question. So let's consider, rather than a single initial configuration, let's consider an ensemble of configurations. And let's ask how this ensemble of configurations evolves in time. And in particular, what I would like to ask is that all of my configurations are confined to a region in phase space. So let's say that here's my phase space, and rather than asking how an individual initial configuration evolves in time, I'll take a bunch of initial configurations which live in some region of phase space. And let's ask how this ensemble evolves in time. Well, at some later time t, each of these individual configurations will be given by some other configuration. So, for example, this dot here might correspond to that one, and after some time t, these may all be given by some configurations, which, even though the initial configurations could have been quite close to each other in phase space, the final configurations could be quite far from each other. And so if we start out with some initial configurations given by some blob on phase space, then at some later time, they'll be contained in some blob in phase space, which might have a very different shape. So let's ask how this blob evolves in time. And the result that I would like to present, which I think is rather amazing, and goes under the name of Liouville's theorem, is that the area of the blob is constant in time. Even though the shape of the blob changes in time, the area is constant. And this can be thought of as a consequence of the fact that the Hamiltonian generates a canonical transformation. So I would now like to give you a somewhat sketchy proof of this statement. But before I do so, are there any questions? Yes? Just consider a area in phase space, a set of points in phase space that make up some surface. So it would be a two-dimensional blob for a two-dimensional phase space, a four-dimensional blob for a four-dimensional phase space, and so on and so forth. And then just evolve each of those points in the phase space for some time t, and then the claim is that the area of that blob does not change in time.
So, like the area is fully made up of blobs, fully covered in blobs?
Yeah, you could imagine a blob which is sort of densely covered by initial configurations. And when I say area, I mean n-dimensional area. You know, two-dimensional area in the two-dimensional case, four-dimensional area in the four-dimensional case. So a four-dimensional area is what you would call a four-volume or a hypervolume or something like that. The thing, yeah. Was there another question? Yeah. So what I would like to do is just prove this to you in the two-dimensional case. And the higher dimensional case proceeds in exactly the same way. So, to prove this to you, before considering a blob of arbitrary shape, let's consider a blob which is a little square. And I'll take it to be a very small square. And I'll take the lower left-hand corner of the square to be given by coordinates in phase space q and p. And I'll take the length of the sides of the square to be delta q and delta p. I guess it's a rectangle. I'm not assuming delta q is equal to delta p. But it's a very small rectangle. And let's ask how this square evolves in time. So, because this square, if we want to understand how the shape of this square evolves in time, then the first thing that we should do is understand how the four corners of the square evolve in time. And let's just evolve a very short amount of time dt. So how does the lower left-hand corner of the square evolve? Well, as we have learned, q and p goes to q and p plus, so q goes to q plus dt times the derivative of the Hamiltonian with respect to p, which, as before, I'll just abbreviate by h sub p. And likewise, p goes to p minus dt times h sub q. Okay, that was easy enough. That was just the form for the Hamiltonian evolution as a canonical transformation that I just presented to you. So that's how the lower left-hand corner behaves. How about the lower right-hand corner? So here we have the point q plus delta q, comma p. So how does that evolve? Well, it's the exact same expression, except now everything is evaluated at the point q plus delta q rather than at the point q. So if delta q is very small, because I'm considering a small rectangle, then I can Taylor expand around the point q. And so I get q plus delta q plus dt times the Hamiltonian, the derivative of the Hamiltonian with respect to momentum at the point q plus delta q, which, if I want to write that in terms of the derivative of the Hamiltonian at q rather than q plus delta q, I need to use Taylor's theorem. And so I get the derivative of the Hamiltonian with respect to p at q plus something proportional to delta q. Plus higher order terms in the Taylor expansion, which I neglect because the size of my square is very small. And likewise, the p coordinate will be p minus dt times the derivative of the Hamiltonian with respect to q, evaluated at q plus delta q, which is h sub q plus the second derivative times delta q. So that was how the lower right-hand corner evolved in time. How about the upper left-hand corner, q p plus delta p? Well, again, this is q plus dt times the derivative of the Hamiltonian with respect to p, evaluated at p plus dp, which is the derivative of the Hamiltonian at p with respect to p at the point p, plus a correction term proportional to delta p. And likewise, p goes to p minus dt times hq plus hqp delta p. Plus delta p here. And finally, we have the upper right-hand guy. How does that evolve? Well, we have q plus delta q plus dt times now the sum of three terms. So we have an hp, an hpp delta p plus hpq delta q. And in principle, of course, there are terms that are higher order in delta p and delta q, but we neglect those because the size of the rectangle is very small. And the p coordinate is p plus delta p plus dt, minus dt times the derivative of the Hamiltonian with respect to q, evaluated at q plus delta q and p plus delta p. Okay. So what does that mean? That means that after a time dt, we started out with a rectangle whose sides were given by whose sides had length delta p times n delta q. And after some time dt, we evolved to some sort of trapezoid, and we can now compute the lengths of the sides of that trapezoid. So if we want to compute the length of the side of the trapezoid, we just need to compute the coordinates of those points here and subtract off the coordinates of that point there. And so what is the length, say, of this side? Well, we take the lower right-hand point and subtract off the lower left-hand point, and we get delta Q. So we subtract this guy from that guy. So we get delta Q plus dt HPQ delta Q, and dt times HQQ delta Q. Everyone with me so far? So all I did was calculate the difference between the position of this point here and that point there. And likewise, if I want to compute the length of that side, I compute the difference between this guy and the original point, Q plus delta Q and P. So what's that guy? Well, that is dt times delta P HPP, and delta P minus delta P dt HPP, HPQ. Okay, so that tells us how this square evolves in time. So what is the area of the square? So the initial area was equal to delta P times delta Q. And after a time dt, what does this area become? Well, it becomes, so if you want to compute the area of a trapezoid, you just take the two vectors that make up the two sides of the trapezoid, write them in a matrix, and compute its determinant. So I'll pull out an overall factor of delta Q, delta P, and we have the determinant of the matrix 1 plus dt HPQ and dt HQQ on the upper row coming from this vector here. And then the other the lower row comes from that vector there, which is dt HPP and 1 minus dt HPQ. Now, everyone with me so far? Okay, so that is equal to delta Q, delta P, times, let's compute that determinant, we have 1 plus dt HPQ times 1 minus dt HPQ. So that's 1 minus dt squared HPQ squared minus dt squared HQQ HPP. Or, in particular, we see that under a time evolution, the area is delta Q, delta P, plus terms of order dt squared. So to linear order in dt, the area is unchanged. So this area is unchanged to first order in dt. So the area goes to the area plus terms of order dt squared. And another way of saying that is that the change in the area with respect to time is equal to 0. So dA here is the difference between A and A at t plus delta t. And so because that difference was ordered dt squared, dA by dt is equal to 0. So we have proven this only for a small change in time dt, but of course we could integrate this with respect to t to show that the area is a constant for all time. Now, of course, I have only proven this to you for squares, and life is more complicated than just squares. But you could imagine that you have an arbitrary shape. So you could have a blob of some very complicated shape. And all we do in order to prove the general result is you think of that blob of some arbitrary shape, and you imagine dividing it up into very small squares. Right? This is how you always prove things in calculus. You divide the blob into very small squares. And because each of the small squares has an area that remains constant in time, so must the blob. And to prove your result formally, you would sort of take a limit where you break up this blob into smaller and smaller squares. You know, this is not a math course, so I'm not going to do that, of course. But, you know, at the level to which we ever prove anything in a physics course, I claim Liouville's theorem is now proven. So, the argument, again, is just based on the statement that to first order in dt, one can compute the change in the area of a small square and see that it vanishes to first order in dt. So dA by dt vanishes, the area is a constant in time, and then you just imagine generalizing this to something of arbitrary shape. And now, of course, you could imagine trying to prove this in n dimensions. And so in n-dimensional systems, the proof is very much the same. Any questions on that? So the n-dimensional volume remains constant in time. Now, I should make an important point here, which is that even though the area or the volume of the blob remains unchanged, its shape does not remain unchanged. And so the shape of the blob does change in time. So typically what will happen is you could start with a blob in phase space that's nice and compact. And as you evolve later in time, the area of the blob will remain unchanged, but the shape will get crazier and crazier and crazier. And so, you know, you might have some complicated spiral, or you might have some, you know, big tendrils. I mean, usually that's what happens. You know, somehow you'll have lots of little small tendrils that creep everywhere over phase space. And so the area will remain constant, but the shape will change. And I should emphasize, well, let me ask the following question. What do you think happens to the area of a blob in phase space under a canonical transformation? So how many people think the area of a blob in phase space could change under a canonical transformation? How many think it can't change? Okay, good. Indeed, the only thing that I ever used in this proof was the fact that q went to q plus dt times the derivative of some h with respect to q. I never used any properties of the Hamiltonian. H could have been any function. And so in particular, what this shows is that under any canonical transformation, the area of some blob in phase space will remain constant. I mean, this is rather remarkable. I mean, it's a sort of remarkable thing that you can prove some fact about every mechanical system, every dynamical system, no matter how complicated. Now, you can prove it to be sure, but whether or not it's useful is another question. And so that brings us to the next sort of fundamental result in the theory of dynamical systems that I would like to present, which is the Poincare recurrence theorem. I won't have time to do it justice in the remainder of class today, but the basic idea is the following. So when we proved Liouville's theorem, we showed that the area of a blob remains constant, but its shape can get very, very complicated. And the essence of the Poincare recurrence theorem is not only does the shape get complicated, but the shape must get very complicated. Exactly. So what does it mean for the shape to get complicated? So if you start out with an initial blob in phase space, which is very small and compact, then that means that all of the initial data that you're considering are very, very close to each other. But then, if at some later time this blob has crazy tendrils that reach all over the place in phase space, that means that the end state of the system could be very, very sensitive to the initial configuration. A very small change in the initial configuration will lead to a big change in the final configuration. And indeed, the essence of the Poincare recurrence theorem is the statement that this not only can this occur, but generically this must occur. Now, when I say generically, I mean unless there's a symmetry or some other very special property of the system which prevents this from occurring. Any questions on that? It's been a big day here in classical mechanics land. We've understood a lot of things. So maybe rather than trying to cram something into the last minute and a half, maybe I'll just pause once more and see if there are any questions and then let you go. Yes?
So the blob may get stretched and everything, but it's always going to, if it starts simply connected, it's going to stay simply connected.
Correct. Yes. Why does it stay connected?
Yeah, like how do we define the blob or define its ensemble of systems?
Well, I mean, I wanted to think about the blob as an ensemble of systems, but I could also think about the blob as some continuous distribution. You could just imagine the following. Just take a region in phase space and shade it some color. Green. Okay. Then ask how all of the green points move as a function of time. Or in fact, you can show that, I mean, it's just because what we're doing is we're studying some smooth evolution process where everything is nice and continuous. That means that you can't break off little bits of this blob. That's not a very precise statement, but it's true. I mean, there's another way that I could have proven this Liouville's theorem. Maybe next year, if I'm bored, I'll try and prove it this other way. Or maybe you all should try and prove it this way. So you could imagine rather than talking about a blob, you could talk about a curve, which is the boundary of the blob. Then you can ask how this curve evolves in time. So this curve is some function, can be thought of as some function p of q in phase space. And then what is the area of inside that curve? The area inside that curve is the integral of p dq. And so you could show that this area is unchanged under time evolution. Because you know how P transforms, you know how Q transforms. Indeed, next week we'll discuss integrable systems in some detail, and we'll do essentially that computation. But one thing that you can see is that the shape, the curve, which gives you the outline of this blob, will have to change in some smooth manner. And so in particular, it can't pinch off in some way. It can get very, very close to pinching off, but it will never pinch off. Any other questions? All right, go harass David Gross.